Yes, so I have the pleasure to talk about methanol synthesis in order to show you how to use the virtual system components that Moritz already introduced nicely. And again, this is also what Philip already had. This is what we are talking about. Why do I talk about methanol synthesis? This is methanol. I hope all of you know this. Methanol synthesis is produced about 100 to 120 million tons per year, so quite a lot of amount of methanol. Because methanol is quite useful. You can use it as chemical building block for fuel additives or resin. And how methanol synthesis usually works is that you have a reactor, methanol, and input. And you have CO hydrogenation, CO2 hydrogenation, and the reverse water shift reaction. And if you do this, usually what comes out is between 2 to 6 mole percent methanol and N2 and CH4 and so on. And this is the process that is usually used to synthesize methanol. This is a process that looks a lot like you can just use FactSage to do it. And if you do this, you can, for example, select this kind of input and select conditions like 250 degrees C and 32 bar. And then what you should get out is 2 to 6 mole percent. So what I do is I calculate this. And what you can see here is my result of this calculation. And you can see that it is 5.64 times 10 to the power of minus 9 mole. That is not really 2 to 6 mole percent. So probably there is some kinetic limitations in my methanol formation that somehow are not considered in my calculation, and this is what I'm going to talk about today. So how can we consider this in order to actually be able to reproduce what we see in the experiments? So, first thing that I have to do is identify the kinetic system. The first that I can do is I can look at my output and see, okay, I put 12 mole N2 in and I get approximately 12 mole percent out, not exactly. And if I look into experiments, it's exactly that. I put 12 mole of N2 in and I should also get 12 mole out. So the first thing that I want to do is that the breaking of the N bond is somehow kinetically constrained, so that it requires more thermal activation to actually be broken. And in order to implement this kinetic constraint and not having all these CH5N and so on formed, what I do is I can go into the phase selection, also what Philip explained to you. And what I do then is I look at the phases that I have. I see here N2, and this is also what I want to keep. What I don't want to keep is everything else that contains an N, and I kick all of them out. Okay. So then I have considered this kinetic constraint. Then we can continue with the next. The rest of it lies all in this phase diagram. C, H, and O, because N I do not consider for now. And if we take a look at this phase diagram and we put in all the species that are in the input, then they are here. And this is methanol, and this is the output that I would like to have. And these are the reactions that are happening in order to produce methanol. That's why I have this nice line between the components that I put in and the ones that I get out. And then there's a lot more that are appearing in my calculation in the end that I get out. They also lie in this nice triangle of C, H, and O. And the question is this reasonable and what happens to them? The first thing I would like you to focus on is these two. So there's a lot more than I showed, but we have used these as example. And what both of them have is no O. So somehow the CO bond was broken. But I do not observe any kind of these species in an actual experiment. So somehow the breaking of the CO bond seems to be, again, kinetically limited, and it seems to require more thermal activation in order to actually proceed. That's why I, again, try to implement these constraints by going into the phase selection. I select everything that does not have a CO bond and get rid of it. Then I'm also okay with the second constraint. Now let's look at the third one, and we see there's more species here. These two I marked now, and what all of them have is more than one C. So they have C bonds between two C atoms. And these I also do not observe in experiments, and this also means that the formation of these C-C bonds is somehow experimentally hindered. So again, same thing, go into the phase selection, select everything that has double C, and scratch it. The final thing that is left is I have an input of 6 mole CH4. And if I look at the output, then I also have CH4 here, and CH4 is lying in my diagram also here. If I look at the experimental results of these reactions, what I see is that I actually do not form any CH4, but the input that I have, and the CH4 that is put into the input does also not decompose. So somehow also this is something that I need to consider as a kinetic constraint. The problem with this is, you see CH4 is the input, so I cannot just kick CH4 out. It lies in this COH plane, and that's why I need to somehow consider it in a different way. And the way I can consider it is by using QA. And it's the same that Moritz already showed you. I just take this triangle that I have and take it to a fourth axis, the QA. So I use virtual system components and add a virtual system component of QA to my CH4. With this, I move it away out of this CHO plane, because now it has the exact same thermodynamic properties as CH4, but it contains this virtual system component, so it cannot be formed out of the CHO system alone. And this I can just do by specifying in the input to Equilib the CH4 QA instead of CH4, and then I can also account for this kinetic constraint. Of course, I can tell you now this works, and we can all be happy, but I can also show you that it actually works. So again, I have this input, and I use FactSage, but this time with proper phase selection and with the virtual system components. And what I get out is this. You see in the bottom there is 7 mole of methanol that actually are going to be formed based on the input that I have implemented now. So a lot more than I had before. This, of course, is an upper limit. I implemented all the constraints to the maximum extent that is possible. Of course, this doesn't need to be the case actually. They can also be only kinetically hindered, and they don't need to be fully suppressed. But I know now that the upper limit is 9 mole% of methanol formation in this process. Again, like I said, in experiments, usually you have something between 2 and 6 mole%, and what you also see is that there is this empirical rule that seems to be valid, that this ratio that you see here at the bottom is supposed to be 2 or around 2 in order to have the maximum methanol output. And also this we can somehow confirm with our calculations, because we can just vary our input, and with the varying input, we can look at what this ratio actually does for the amount of methanol formed. Again, here I use the assumption that the CO2 content is constant, because then I only vary the H2 and CO content. And you see that the maximum is somehow reached directly before it reaches 2. So it seems to be that we can reproduce this empirical rule that they have in the experiments as well. And with this, I showed you a very quick example of how to use virtual system components in this. And if you want to learn more, there's 2 more talks by Moritz and Joao about this. And I think Joao is next.